All right, this PowerPoint is on energy conservation for AP Environmental Science. We're going to be looking at the last learning objective for this unit, which is energy conservation, and we're going to describe methods of energy conservation, keeping it pretty broad, and also talking about some specific things. Here's the vocab slide. And before we get into energy conservation itself, I want to talk about life cycle emissions for various energy resources. So when it's talking about life cycle emissions, we're going to be talking about CO2 emissions or CO2 equivalents. So remember that every single greenhouse gas has its carbon dioxide equivalent, and carbon dioxide is set at 1, and all the other greenhouse gases are based off of carbon dioxide. So for example, nitrous oxide is 250 times stronger of a greenhouse gas than CO2. So its CO2 equivalent is 250 or 252, something around there. And it will be factored into these as well. So if we have nitrous oxide emissions, if we have methane emissions, in this case, we're talking about albedo as well. So the reflectivity of a surface. All of these are going into this chart. And the median emission is what it's ranked off of. You can see that coal, gas, biomass are the highest, coal by far the most, and then natural gas, and then biomass. So dedicated biomass for energy use in a power plant. So this would be trees or other biomass that's grown specifically for being ground down into pellets and then used into a power plant. So those are our three highest ones here. Unfortunately, this diagram doesn't talk about oil because it's too broad. We're talking about, gasoline and diesel and heavy fuel oil. We're talking about diesel burning power plants and transportation. All of those things, I imagine that's why it's not on here. But oil would be in here between coal and natural gas. Okay, so the fossil fuels by far have the most CO2 emissions. And then going down from there, we get into our renewables and into our alternate energy sources. So solar photovoltaic, these do have large life cycle emissions relative to the other renewable and alternative energy sources, because you have to mine all the materials for the solar panels, assemble them all, and then they only have a 20 to 30, 50 year lifespan. And after that, they become waste that can, in theory, become recycled, but it's difficult in practice. Geothermal, concentrated solar, hydropower, going down from there. You notice that wind and nuclear are the lowest. And we see the same thing on the diagram on the right, but in a a chart form, a graph, and we see oil right there. That's an oil-fired power plant. So not talking about transportation, but power plants. So if we're talking about reducing greenhouse gas concentrations, the biggest things that we can do are reducing the amount of coal, oil, and natural gas that we're burning, because you notice in this graph, they are by far the most, and they're the only ones, in addition to biomass, that release carbon dioxide into the atmosphere. And biomass, remember, is carbon neutral unless you're digging up peat or old growth forests. And we see a very similar trend with deaths per terawatt hour, the safety of these energy resources. Coal, oil, biomass, and natural gas are the most polluting energy resources. And remember that millions of people die every year from air pollution. So this is what we're talking about with those lives that are cut short from cancers, respiratory illnesses, cardiovascular illnesses due to pollutants. So coal, oil, and natural gas and biomass are by far the most polluting and are causing the most deaths per terawatt hour. So we see the same trends with human health. So that brings us to energy conservation. Because we want to reduce the amount of carbon dioxide that we're putting into the atmosphere to meet climate targets and to reduce the effects of global warming and global climate change, and because we want to phase out coal, oil, and natural gas because they're finite resources and there is not that many years of them, that many decades of them left on the planet. We want to avoid the economic consequences of that. And because of their polluting effects on human health and the environment, we need to talk about energy conservation. So all of the energy sources have their own positive and negative aspects, but energy conservation as a whole is crucial. When we're talking about energy conservation, some people will talk about the energy pyramid. At the energy pyramid, the base of it is what we could do every day in our day-to-day lives. We can just use less energy. We can conserve energy. That would be things like turning off the lights when you exit a room, adjusting the thermostat so it's not quite as warm in your house. The hot, like the furnace isn't working as hard in the winter, or it's not as cool in the summer. The air conditioning isn't working as hard and drawing as much power in the summer. Um, it could be alternate transports. So instead of driving 2 miles to school, you could bike instead, given what the weather is like. Energy efficiency is the next tier up in this pyramid, and that's looking at energy efficient appliances. That could be Energy Star appliances, which is a federal program that ranks energy efficient appliances and gives them the Energy Star if they meet their qualifications. And that could be for any type of appliance. That could be for a refrigerator, dishwasher, a hot water heater, etc. And then the last one is something that we could do both on an individual and as a government or societal scale, and that's switching to renewable energies. Okay, and in the renewable energies, I would also include the alternate energy nuclear, which is a non-renewable energy, but is non-pollutant and does not release carbon dioxide or any other greenhouse gas into the atmosphere. So in addition to that, briefly, think about what you can do on an individual scale to conserve energy. What can you do in your day-to-day life as a individual citizen to conserve energy? And then what can we do on a societal or global scale? Okay, so think about this for a couple seconds, pause the video. Okay, so what can we do on an individual scale? Well, a big thing is switching to renewables. Now, this may be impractical for some people. There's the cost that's associated with it, and there's the logistics associated with it, but people can add solar panels to their roofs. You can even, especially in more rural communities, have small scale geothermal or small scale wind or even small scale hydro given proper permits. But that does come with an upfront cost, which is why we also need for the government to help out with that with subsidies um, to make it affordable for people and economically incentivize people to put solar panels on their homes. Even if it's a small scale, like passive or active solar, that like a solar heater or building design, that can still have a big impact and still reduce a individual's energy use. Using less, this one is often touted as like the way to solve the entire problem, but it is absolutely not. Individually, we do use a lot of electricity, but that amount of electricity is rather small compared to what's used in citywide landscapes. So yes, the individual home or an individual office building, people can turn off the lights when they exit a room. Um, all of those small little amounts of electricity that are being saved do add up, and at a large scale that means that we don't have to burn as much natural gas. If everybody was to turn off all the lights when they left the room, or if they were to all adjust the thermostat so it's not using quite as much energy, that does have a um, significant output back at the power plant, so that we're burning less natural gas, less coal, less diesel, and if everybody in the society was to do it. But it's still not going to address the fact that they're burning coal or diesel in that power plant. In fact, on countries that are pretty much exclusively renewable, like Iceland is 70% hydroelectric, 30% geothermal, nobody feels guilty about keeping the lights on or having as much light as possible or having a lit greenhouse during the winter or having the heat turned up because they do cogeneration. So if we switch to renewables as a society, yeah, using less energy would be good because we don't need as many solar farms or as many wind turbines or as many hydroelectric dams. But from a pollution standpoint, it doesn't really matter. But anyway, we'll keep going with it. Switching to energy efficient appliances. This is something that we can easily do at the home. There are even grants or subsidies, like rebates for for energy efficient appliances. Again, adjusting the thermostat. You don't need to wear a short sleeve shirt in the middle of the winter. You can wear a long sleeve shirt indoors, even maybe a sweater indoors. That doesn't need to be 80 degrees in the house during the winter. You could be at 70 degrees, 65 degrees. I don't even have central heating and cooling in my house, so I'm very cognizant of the heaters that I turn on, and I turn on very few, and I'll just wear a sweater indoors, and when I sit down on the couch, wrap up in a blanket. It doesn't bother me. During the summer, like open the windows rather than the air conditioning. Now that's here in Colorado, where it's a relatively dry heat in the summer. That'd be very different from somebody that's living in the South that has a very humid, hot summer. And in fact, the population of the South is only rising because we have air conditioners. That's why so many people are moving there. Conserving water, it takes energy to heat water, to cool water significantly, to filter water and purify and pump water from the municipal supplies. All of that uses energy. And that brings us to landscaping. It does take a lot of energy to get our water to our homes via pumping systems. And the more water that we're filtering, cleaning, and pumping, the more electricity that we're using. And then using public transportation or alternative transportation that includes walking, biking, skateboarding to school, whatever that you're doing to not burn oil products in an internal combustion engine. And then awareness and advocacy is always good, but can only get you so far. From a societal and global scale, investing in renewables. Again, Iceland, it doesn't matter if somebody's turning on the heat really high. I mean, they have cogeneration, which I'll talk about next, but they are 100% renewable, so nobody's really bothered by excess electricity use. Same thing with France. France is 75% nuclear, 20% hydroelectric. You can turn on the appliances to their highest setting in France, and it's not really going to make too big of a difference in terms of greenhouse gas emissions. Improving fuel economy for vehicles, we'll talk about that in a little bit. We'll talk about battery electric vehicles, making public transportation more economical, reducing the stigma around public transportation, proper urban planning, green building design. Proper urban planning could include stuff like making small localized neighborhoods within cities so that people live next to where they go to work, where they go to school, where they shop, where they find entertainment. They have all of that within a small radius and don't have to rely on any type of transportation other than walking, biking, and local public transportation to meet those needs. Carbon capture technology is huge. We'll talk about that on another day. And then, or investing in carbon capture technology, and then stabilizing population growth, because ultimately the more people that you have on the planet, the more energy that you're going to be using. So let's talk about a few of those things that we need to talk about with energy conservation to just wrap up some loose ends. And the first one with that is cogeneration. This is using the energy for 2 or more simultaneous applications. So this is most commonly used for electricity and heat. Let's say that you have a geothermal power plant like they have in Iceland. The geothermal power plant is going to be pumping that hot water from the inside of the earth, turning to steam. Steam turns a turbine, generates electricity. That's the first application of that hot water. It's turning a turbine in the form of steam to generate electricity. Well, to turn a generator to generate electricity. I don't want to ever leave that point off because you shouldn't on an AP test. But what do you do with that hot water? Well, what they do is they, in Iceland, is they pump it, at least in some of the power plants, many of the power plants, they pump it as hot water in insulated pipes to the town. And in the town, they distribute that hot water to all of the buildings, and they give people very, very cheap, readily accessible hot water. You don't have to wait for the hot water tank in the basement to heat up your water in Iceland because there is no hot water tank in the basement. And of course, I'm generalizing for an entire country. Because you just turn on the tap and you're pumping into this, or you're tapping into this hot water supply that's coming from the power plant that's ready and at pressure. They also have hot water heaters in all the rooms. So the radiator heater that's on the wall has hot water going through it, and that hot water is coming from the cogeneration power plant, and you can turn the hot water on as hot as you want because it's just within a closed system, and hot water from the power plant and then returning it back to the power plant once it cools down. So that's cogeneration. You're sending hot water via insulated pipes to the town so that they have cheap hot water that they can use for cooking, bathing, domestic use, and as heat. You can have hot water that is in insulated pipes or heated pipes that are underneath the floor, so you have under like subfloor heating for a home. It doesn't have to be a radiator on the side of the room on the wall. That's actually relatively common throughout Europe. Countries ranging from France to Russia will use cogeneration and have hot water supplies going to local buildings. Probably the most familiar example that you know of is the heat from your engine in your car. So if you have an internal combustion engine in your car, that generates a lot of waste heat. One way that we can use that heat is during the winter, you turn on the heater on the car, and all that does is turn on a fan. It doesn't turn on some type of machine that creates excess heat or more heat. You're just using the hot air that's coming from the engine and blowing that into the car. It does not contain any emissions. It's just heat, it's just hot air. And you're just blowing it into the cab of the car and using the hot engine to heat up the cab of the car. That's why it takes a little while for the heater to really kick on, because it takes a little while for that engine to really start producing enough heat from the burning of fossil fuels, oil products, to heat up that car. Okay, so that's cogeneration. Usually we're going to be making electricity and heat, but we can also be doing this in a manufacturing facility and getting heat, but it's typically electricity and heat. In terms of vehicles, there are 3 or 4 things that we could be doing and are doing for energy conservation with transportation. The first is setting CAFE standards. Now, this is one of the pieces of legislation that you do need to know for the class for the AP test. CAFE standards, corporate average fuel economy standards. This sets fuel economy standards, so like mile per gallon standards in the United States for car makers to do business in the United States. If a company is going to sell a vehicle in the United States, they have to meet these fuel economy standards so that they can sell these vehicles. We'll talk about them in a little bit more detail in the next slide, and we'll talk about some trends in the graphs over time for CAFE standards. But different countries might have stricter, more loose standards, but this is essentially saying that you need the vehicle to meet this specific miles per gallon or better in order to be able to sell a vehicle here, so that they don't pollute as much. They don't release as much carbon dioxide per mile because you're not burning as much fuel per mile. But it's also because of the other pollutants that are released as well. Battery electric vehicles, these are vehicles that run completely on a battery. They're the ones that you plug in and they charge up via electricity from the grid. They don't produce any emissions during their operation, but they do have the ecological footprint from the materials that they need to mine to make the vehicles, and especially the batteries themselves. And those batteries include lots of lithium and cobalt, among other metals that are required, that all have to be mined and come with their own mining impacts. Also, you have to think about where you're getting that electricity. If you're getting your electricity from a coal burning power plant, and that coal burning power plant is burning brown coal or lignite, which is the dirtiest burning form of coal, it might be as bad as burning a gallon of, like burning gasoline. But if you're getting that electricity from wind turbines and solar panels and nuclear power plant, then it's going to be really, really clean. So we have to think about the lifetime emissions, or the full source of like the use of that vehicle. Hybrid vehicles use both batteries and an internal combustion engine to improve the fuel economy. So rather than getting 30 miles a gallon, they might be getting like 70 miles a gallon, because they are using the battery in the city or when they're idling, and then they'll be using the internal combustion engine when they will be you know, ramping up, accelerating pedal to the metal, and then they'll switch back to the battery when they're just cruising. So they can also, as well as battery electric vehicles, many of them, both of these will get excess charge for or will recharge the battery through regenerative braking, where they essentially use the friction from braking in order to convert that energy into electricity to recharge those batteries in both battery electric vehicles and hybrid vehicles. If you wanted to add one more thing for energy conservation of vehicles, you could think about hydrogen fuel cell vehicles, but we're not really there yet as a society, and I don't think that we're going to be using them anytime in the near future. So an internal combustion, you should know very, very generally what an internal combustion engine does. You don't need to reproduce, or you will never see one of these diagrams ever, but just know that you burn gasoline or diesel and that you're going to be powering this vehicle. And I'm not even going to talk about how this works because you really don't need to know it, so don't even worry about it. But CAFE standards you do need to know. So with this diagram, we're seeing CAFE standards for cars and light trucks. We see the dashed line, which is the real, actual what's going on in the world, and then the standard is what is being regulated, what the regulation is. So CAFE standards were passed in the late 70s. You don't need to know the dates for any specific piece of legislation in this class. You just need to know what they do. So they were passed in the late 70s, and very quickly we see that if you just focus on the solid line for cars, that the CAFE standards for cars increased dramatically. Industry was told by the government that they had to create more efficient engines, and they did. And they absolutely have the technology today to create even more efficient engines than we have today. You notice that there was a dip in the CAFE standards for cars in the late 80s and then increased back up to what it was in 1985 by 1990. There are political reasons for that we're not really going to get into, but I'm sure that you can understand what was going on there. You see that they stagnated throughout the 90s into the 2000s until the late 2000s, around 2010, where there was a big push to increase fuel economy standards for cars again. Today we have the technology to make it to where every single car in the United States, every new car that is sold in the United States or manufactured to be sold in the United States can get over 40 miles a gallon, but we just don't do that. We don't regulate it that way, and then they therefore don't sell it that way. That has a lot to do with lobbyists from the fossil fuel industry that don't want it to be that way. Same thing with light trucks. We could be getting way more than 25 miles a gallon for light trucks. The technology exists, but the industry has pushed back and has kept these CAFE standards lower than they could be given the current technology. And this is obviously in the interest of the fossil fuel companies that want to sell more fuel and therefore make more profits. The downside of that is that it leads to more carbon dioxide and other emissions. And then one last thing about CAFE standards for fuel economy is that they just talk about carbon dioxide emissions. They don't talk about emissions of anything else. So if you've ever done an emissions test for particulate matter, nitrous oxides, any other types of emissions or pollutants, those aren't regulated on CAFE standards. Those are just miles per gallon standards that specifically just talk about how many miles you can go on a gallon of gasoline. It doesn't even really tackle the problem of carbon dioxide other than incidentally. All right, so battery electric vehicles, the point of this is just saying like we need a lot of materials to make battery electric vehicles. There's about 29 kilograms of nickel in a battery. In a battery electric vehicle. Sorry, is this just a battery? No, it's just the battery. So 29 kilograms of nickel. We need 35 kilograms of aluminum. We need 20 kilograms of copper. Like these materials are becoming increasingly rare as we use more of them around the planet. If we're looking at manganese, cobalt, 10 and 8 kilograms respectively, 6 kilograms of lithium. Lithium is relatively difficult to mine and comes with a lot of mining waste. Um, so there's a lot of materials in a battery electric vehicle that have to be mined, and given the current technology, there's no two ways around that. So hybrids, battery electric vehicles, CAFE standards, they are great. I don't want to like make it sound as if they are negative things, but especially battery electric vehicles, they are great. There's a article that you can read on Schoology about how a couple years ago Norway became the first country where over 50% of its sales were from battery electric vehicles. That's huge. That's reducing the amount of greenhouse gas emissions from transportation, but you also should be thinking of increasing public transportation, walking and biking, um, you know, all of those different things besides individual transport. But battery electric vehicles, hybrids, those will definitely get you the points on the AP test, given the proper prompt and answer. Green building design, so we could be talking about passive solar, we could be talking about solar lighting. Grandview is actually really good for solar lighting. We have a lot of natural light, especially in the main hallways. The gymnasiums have the skylights, so we have to use less artificial light in this building because we have so much solar lighting. Proper insulation. Proper insulation is huge. That can be one of the biggest things that an individual homeowner can do to reduce their fuel use. Um, is properly insulating their home. If you're losing a lot of heat during the winter to the outside environment, you have to keep the heaters working harder and faster and using more electricity. And same thing with cool air in the summer. If you're losing a lot of that, you're running the air conditioner longer. Green roofs have a huge insulative capacity, and they have a lower albedo than asphalt. Or sorry, they have a higher albedo than asphalt. They reflect more solar radiation than asphalt, and they have a net cooling effect on the surrounding area, and they clean water as well. Active technologies like active solar, solar photovoltaics, those can be incorporated into green building design as well. And then green engineering, we're not really going to talk about. It's not part of the learning objectives, but I do just want to mention it. It's a way of improving our engineering technology right now so that everything that we do is more efficient. If you are producing X, Y, or Z in the factory, what can you do along that factory line to make that more efficient, to pollute less, to make everything more quote unquote environmentally friendly? All right. So hitting the learning objectives, some methods for conserving energy around the home include adjusting the thermostat, conserving water, use of energy efficient appliances, and conservation landscaping. And again, one more that you can add there is proper insulation. Methods for conserving energy on a large scale include improving fuel economy for vehicles, using battery electric vehicles and hybrid vehicles, using public transportation, and implementing green building design features. All right, let me know if you guys have any questions, and I'll see you all in class.